Since the first human glances toward the night sky, one question has echoed silently across civilizations, religions, and philosophies. Are we alone in the universe? This question is not merely scientific, it is deeply existential. It strikes at the very foundation of our understanding of humanity's place in the cosmos. Ancient Babylonian, Egyptian, Greek, and Mayan cultures saw gods and spirits in the heavens, yet they also left records of their unease about other forms of life. Thinkers from ancient Greece, such as Epicurus, speculated about multiple worlds inhabited by diverse beings. As science progressed, the question moved away from mythology and philosophy and entered the domains of astrobiology, astronomy, and cosmology. The vastness of the known universe, with its trillions of galaxies, each containing hundreds of billions of stars, suggests an almost infinite range of possibilities for life to flourish elsewhere. And yet, so far, all we have is silence. The 20th century was marked by an explosion of discoveries that transformed this question into a serious scientific pursuit. The discovery that other planets orbit distant stars, the so-called exoplanets, opened up a new field of study, exoplanetology. With the launch of telescopes like Kepler, and more recently the James Webb Space Telescope, astronomers began observing not only distant stars, but also the worlds orbiting them, measuring their masses, atmospheric compositions, and in some cases even signs of potential habitability. The question shifted from, are there planets out there, to, can those planets harbor life? Science no longer gazes at the sky in contemplation alone. It now probes it with instruments of precise calibration, scanning the heavens for any signal, any spectral anomaly, any noise that might indicate we are not alone. The human fascination with the idea of cosmic companionship stems not only from a desire for adventure or discovery. Embedded within that longing is a deep search for belonging and meaning. If life emerged only on Earth, on a tiny dot within a vast universe, that could suggest we are an absurd exception, a statistical anomaly. But if life is common, scattered across countless forms and environments, that not only transforms our understanding of biology, but also redefines the philosophical implications of our existence. The mere fact that we have not detected any form of life, intelligent or microbial, raises implications that split scientists into two broad camps. The optimists, who believe that absence of evidence is not evidence of absence, and the pessimists, who see the silence as possible confirmation of our cosmic solitude. Beyond the search for microorganisms, there is the even more complex challenge of detecting intelligent life. Since the 1960s, programs like SETI, Search for Extraterrestrial Intelligence, have scanned the sky for radio signals or transmissions that might indicate the presence of technologically advanced societies. So far, none of these signals have been confirmed. In 1977, a radio signal picked up by the Big Ear radio telescope at Ohio State University, known as the WOW signal, offered a fleeting spark of hope, but it was never repeated. Even so, the search continues. New projects using more sensitive telescopes, such as Breakthrough Listen, are refining the hunt, analyzing billions of frequencies with algorithms capable of processing massive amounts of data in real time. The paradox between the immensity of the cosmos and the absence of evidence is what makes this question so powerful. It is sustained not only by scientific curiosity, but also by its emotional and philosophical weight. The simple act of gazing up at the stars and wondering whether someone might be gazing back is in itself profoundly human. The question of whether we are alone is also a question of who we are. The search for life in the universe is, ultimately, an extension of our search for meaning, and perhaps in finding others we may come to understand ourselves more deeply. Among all the scientific questions that trouble us, few are as mysterious as the origin of life. Around 4 billion years ago, Earth was a hostile world filled with volcanic eruptions, violent electrical storms, and primitive oceans loaded with chemical compounds. And at some moment, within that geological chaos, inorganic molecules began to self-organize until they gave rise to the first forms of life. Science still lacks a definitive answer to how life began, but throughout the 20th and early 21st centuries, significant advances have led to increasingly refined hypotheses about the possible paths that bridge the gap between chemistry and biology. One of the most influential theories is the primordial soup hypothesis, proposed by Alexander Oparin and John Haldane in the 1920s. According to this idea, the primitive atmosphere of Earth, rich in methane, ammonia, water vapor, and hydrogen, reacted with electrical discharges and ultraviolet radiation, promoting the formation of simple organic molecules such as amino acids. In 1953, this concept gained experimental support through the famous Miller-Urey experiment, in which a simulation of the early Earth's atmosphere produced, after a few days, organic compounds fundamental to life. It was one of the most emblematic moments in experimental biology, proving that the basic building blocks of life could form spontaneously under conditions compatible with the early Earth. But the existence of amino acids alone is not enough to define life. The real challenge lies in understanding how these simple molecules came together to form complex structures capable of self-replication and evolution. Several hypotheses attempt to explain this leap. One of the most discussed is the RNA world hypothesis, which suggests that RNA, due to its catalytic and informational properties, may have been the first functional biological molecule. Unlike DNA, RNA is simpler and can act as an enzyme, catalyzing its own replication. This idea proposes that before the existence of cells as we know them, there may have been a prebiotic stage in which self-organized RNA structures could replicate and mutate, a rudimentary mechanism of natural evolution. Another line of research suggests that life may have originated in hydrothermal environments at the bottom of the ocean, where submarine thermal vents rich in minerals provide a constant source of chemical energy and ideal conditions for complex organic reactions. In these deep geothermal fissures, known as black smokers, organic molecules could have formed and been protected from the intense solar radiation that bombarded the surface of the early Earth. Additionally, these aquatic environments provide natural compartmentalization, such as rock pores, which may have served as microenvironments for orderly chemical reactions, approaching the concept of protocells. The origin of life also raises the possibility that the process was not exclusively terrestrial. The panspermia hypothesis suggests that the basic ingredients of life, or even extremely resilient microbial life forms, may have come from space, carried by comets, asteroids, or meteorites. This idea gained traction with the discovery of amino acids and organic compounds in meteorites like the Murchison, and with space experiments showing that certain microorganisms can survive extreme conditions of radiation and vacuum. Although this hypothesis does not solve the mystery of origin itself, it expands the scope of investigation beyond Earth, hinting that life may be a cosmic phenomenon, not just a planetary one. Despite all the progress, the origin of life remains an open scientific frontier. Laboratory experiments have been able to simulate partial steps, such as the formation of proteins, lipids, and even artificial protocells, but the leap from complex organic chemistry to a self-replicating living system remains an enigma. Science is working on multiple fronts to close that gap, combining data from molecular biology, geology, prebiotic chemistry, and astrobiology. And every new discovery about life's earliest moments on Earth not only helps us understand our own past, but also fuels hope of finding similar processes on other planets. For if life could emerge from chaos on our planet, perhaps it also flourished on distant worlds that share the same fundamental conditions: energy, water, and time. In 1961, radio astronomer Frank Drake proposed a formula that would forever change the way science approaches the search for intelligent life beyond Earth. More than just a mathematical equation, the Drake equation is a conceptual model aimed at estimating the number of technologically advanced civilizations that might currently exist in the Milky Way and be capable of communicating via electromagnetic signals. The equation is composed of a series of variables which, when multiplied together, provide a probabilistic portrait of our potential for not being alone. These variables include the rate of star formation in the galaxy, the fraction of those stars with planets, the average number of habitable planets per star system, the fraction of those planets where life actually develops, the fraction of life that evolves into intelligence, the fraction of intelligent civilizations that develop detectable technologies, and finally, the duration of such civilizations. Each variable carries massive margins of uncertainty, but together they create a fertile ground for informed speculation. For decades, Estimates plugged into this equation varied widely depending on how optimistic or skeptical the scientist interpreting it was. Some calculations suggested millions of active intelligent civilizations in the galaxy, while others concluded we might be entirely alone. The philosophical power of the Drake equation lies precisely in this range. It forces us to confront the abyss between statistical probabilities and observable reality. Modern science, especially with data from the Kepler Space Telescope, has become much more accurate in determining the early variables of the equation. We now know that most stars have planets, and many of these orbit within what's known as the habitable zone. This already makes the universe a far more fertile environment than we imagined in the 20th century. However, the greatest uncertainties lie within the biological and socio-technological factors. The fraction of planets where life actually emerges is still unknown, and even more uncertain is the fraction where that life evolves into intelligent forms. Earth's history suggests that intelligence as we know it may not be inevitable, but rather an evolutionary accident. Life appeared relatively quickly on Earth, but multicellular organisms took billions of years to evolve. Technological intelligence, in turn, arose only a few thousand years ago and may represent only a brief phase in a planet's billions of years-long story. This raises the possibility that even on habitable worlds, evolution may follow very different paths or never reach the point of producing conscious, communicative beings. Another crucial factor in the equation is the lifespan of technological civilizations. This may be the most unstable and melancholic term in the Drake equation. Civilizations that achieve interstellar communication technologies might not last very long. The risks of self-destruction, ecological collapse, nuclear war, social breakdown, or climate catastrophe may be high enough to make the detection window extremely short. If each civilization only lasts a few centuries, the chance of two existing at the same time in the vast timeline of the cosmos becomes minimal. This reinforces the idea that the absence of signals may not mean the absence of life, but rather a temporal misalignment. We may be alone now, but not necessarily alone forever. The Drake equation also inspired search programs like SETI and led to the creation of conferences, research institutes, and projects devoted exclusively to astrobiology and extraterrestrial intelligence. Even without definitive answers, it remains one of the most important tools for scientific reflection about the cosmos. Its real value does not lie in predicting exact numbers, but in organizing human thought around the most profound question of all. What would it take for intelligent life to be common in the universe? Every new scientific discovery, whether related to exoplanets, atmospheric biosignatures, technosignatures, or sustainable social structures, becomes an adjustment to the variables in this equation, making it less speculative and more grounded in real data. The Drake equation, therefore, doesn't give us an answer. It offers a map of unanswered questions. It structures uncertainty and guides us through it with clarity. As long as we can't precisely define each variable, the question will remain alive, not as a desperate doubt, but as an invitation to explore. After all, if intelligent life exists in other corners of the universe, it may also have had its own Frank Drakes, gazing at the stars with the same longing we feel today. And that in itself is already an extraordinary thought. On an ordinary afternoon in the 1950s, during an informal conversation among physicists at Los Alamos National Laboratory, the renowned scientist Enrico Fermi posed a seemingly simple but profoundly unsettling question. Where is everybody? What he meant was both direct and disconcerting. If the universe is so ancient, so vast, and if there are billions of potentially habitable planets just in our galaxy, then why have we never detected a clear sign of intelligent life beyond Earth? This question, which would come to be known as the Fermi Paradox, has become one of the greatest dilemmas of modern science. The contradiction between what we statistically expect to find and what we actually observe, absolute silence, lies at the heart of an unresolved scientific tension. The Fermi Paradox begins with seemingly logical premises. The Milky Way is about 13 billion years old, and Earth has existed for only 4.5. Even if technologically advanced civilizations took just a few million years to emerge and expand, that would be enough time for many to have already colonized large portions of the galaxy. Theoretical technologies like self-replicating probes, known as von Neumann probes, could explore star systems in cascades, multiplying and mapping planets with immense efficiency. And yet, no artifact, no unambiguous signal, no trace has reached us. We stand before a universe that seems to scream with possibilities, but in practice remains deafeningly silent. Many hypotheses have been proposed in an attempt to solve this paradox, each carrying profound implications. One suggests that intelligent life is extremely rare, or that intelligence like ours is statistically improbable. Another, known as the Great Filter, posits that there is a nearly insurmountable evolutionary barrier that prevents life from advancing from simple forms to advanced civilizations. If the Great Filter is behind us, that would mean intelligent life is rare, and we are remarkable exceptions. But if it lies ahead, it implies that civilizations tend to self-destruct before becoming interstellar. This interpretation turns the silence of the universe into a grim warning about our own future. Other theories aim to resolve the paradox through sociological or technological explanations. Perhaps intelligent civilizations simply choose not to communicate, adopting a kind of non-interference policy, as proposed by the zoo hypothesis, in which Earth is a sort of nature reserve being observed from afar. Perhaps they use communication methods so advanced that they're invisible to us, quantum signals, gravitational transmissions, or encryption systems we couldn't possibly decode. Another possibility is that most civilizations exist inside computational simulations or have migrated to digital worlds where their activities leave no detectable astrophysical traces. Some also suggest that we may be observing the universe through the wrong filters. SETI and other initiatives focus on radio signals, but maybe we're looking for the cosmic equivalent of smoke signals in an age of fiber optics. Our own technological evolution shows how quickly communication methods can become obsolete. Furthermore, our concept of carbon-based life and intelligence, modeled after humans, may be limiting our expectations. There could be forms of consciousness and communication so radically different from ours that we wouldn't recognize them even if they stood right before us. The Fermi Paradox remains an uncomfortable reminder that, no matter how far we advance in instruments and theory, there is a silent barrier between us and the rest of the cosmos. We do not know whether it is physical, biological, technological, or simply temporal in nature. Perhaps we are alone only for now. Perhaps other civilizations existed and vanished long before Earth even formed. Or perhaps they are out there, silent by choice. In the meantime, we keep listening, attentive, hopeful, and humbled by the silence that surrounds us from every side. Until just a few years ago, the existence of planets beyond our solar system was merely a logical hypothesis, supported by statistics and the belief that the Sun could not possibly be the only one of its kind among hundreds of billions of stars. But it was only in the 1990s that the first exoplanet was confirmed, marking the beginning of a revolution in astronomy. Since then, the search for habitable exoplanets, worlds beyond our own that might host life, has become one of the most fascinating frontiers in modern science. And in this mission, two space telescopes stand out: Kepler and James Webb. The first, launched in 2009, was specifically designed to detect exoplanets using the transit method, that is, identifying small drops in starlight when a planet passes in front of its star. The second, launched in 2021, goes much further. The James Webb Space Telescope is capable of observing the atmospheres of these distant worlds, analyzing the light that passes through them, and detecting possible chemical signatures that may indicate the presence of life. The Kepler telescope turned statistical estimates into concrete reality. During its 9 years of operation, it discovered over 2,600 confirmed exoplanets and thousands of additional candidates. From this data, astronomers concluded that planets are the norm, not the exception. It is now estimated that there are more than 100 billion planets in the Milky Way alone, and that at least 20% of Sun-like stars have an Earth-sized planet within their habitable zone. The habitable zone, also known as the Goldilocks zone, is the region where a planet is neither too hot nor too cold, allowing the presence of liquid water on its surface, one of the essential conditions for life as we know it. But detecting a planet is just the beginning. The next frontier is to understand what lies within it, and that is where the James Webb Space Telescope comes in. With unprecedented sensitivity, it can analyze the light spectra that pass through exoplanetary atmospheres during transit, revealing the presence of specific molecules such as water vapor, methane, carbon dioxide, ozone, and even complex organic compounds. The simultaneous detection of certain gases, especially those in chemical disequilibrium, can be a strong indication of active biological processes. For example, on Earth, the continuous presence of oxygen in the atmosphere is maintained by photosynthesis. Without life, oxygen would react with other elements and vanish in just a few millennia. Therefore, discovering similar atmospheric compositions elsewhere could be the first step in identifying living planets. Beyond atmospheric composition, the James Webb also enables scientists to estimate surface temperatures, planetary densities, and, in some cases, even signs of geological activity. This helps differentiate between gas giants, rocky planets, and deep ocean worlds. Some of the most promising targets so far are the planets in the TRAPPIST-1 system, an ultra-cool dwarf star hosting 7 Earth-sized planets, 3 of which lie in the habitable zone. Other candidates such as K2-18b, LHS-1140b, and TOI-700d are also under close observation. K2-18b in particular drew attention when water vapor was detected in its atmosphere, suggesting the presence of a liquid water layer, although it is still debated whether its structure could truly support life as we know it. The importance of these discoveries goes far beyond the desire to find aliens. They redefine our perception of Earth's place in the universe. For a long time, we saw our planet as a rare jewel, perhaps unique. But the new era of astrobiology suggests that Earth may be just one among trillions. The diversity of exoplanets is so vast that many have no analog in our solar system. There are super-Earths, mini-Neptunes, ocean worlds, planets shrouded in metallic clouds, or with extremely tight orbits around dwarf stars. This multiplicity of environments raises the possibility that life could arise under very different conditions, perhaps even in forms entirely unlike anything imagined by terrestrial biology. As technology advances, new telescopes are already in development, such as the Nancy Grace Roman Space Telescope, and ambitious projects like LUVOIR and HABEX. These aim to search for even more precise biosignatures in Earth-like planets. Astronomy, which once limited itself to observing points of light, now reads atmospheres, estimates pressure, detects organic compounds, and builds thermal maps of worlds hundreds of light years away. The question of habitability has evolved from theoretical speculation into an experimental science in full expansion. And the more we discover, the more the silence of the universe changes, not into absence, but into expectation. A dense, charged anticipation in which every new piece of data might be the prelude to the most revolutionary moment in human history, the day we look at a point in the sky and know, with scientific certainty, that Earth is not the only place where life breathes. In the search for life beyond Earth, one of the most fundamental and at the same time most poetic concepts is the so-called habitable zone, also known as the Goldilocks zone. The name refers to the classic fairy tale of the 3 bears, in which Goldilocks chooses the porridge that is neither too hot nor too cold, but just right. In astronomical terms, this metaphor describes the region around a star where temperatures are suitable for the existence of liquid water on a planet's surface. Liquid water is considered essential because everywhere it exists on Earth, even in the most extreme environments, life is found. The habitable zone, therefore, is the logical and necessary starting point in the search for potentially living worlds. But what determines this zone? The key variable is the luminosity of the star. Larger and hotter stars, such as spectral types A or B, have habitable zones farther away, but they live very short lives, sometimes only a few 100 million years, which may not be long enough for complex life to evolve. Smaller stars, like red dwarfs of spectral type M, live for tens of billions of years, offering vast time windows for biological evolution. However, their habitable zones are very close to the star, which exposes planets to intense solar storms, radiation, and the risk of gravitational locking, a phenomenon that can cause one side of the planet to face the star permanently, while the other remains frozen in eternal darkness. Despite these challenges, the habitable zone is a powerful tool for filtering promising candidates in the search for life. Estimates based on data from the Kepler telescope suggest that there are billions of planets located within this zone in our galaxy. But that does not mean all of them are truly habitable. The Goldilocks zone is a necessary condition, but not a sufficient one. Other critical factors come into play: the presence of a stable atmosphere, a magnetic field to shield against cosmic radiation, tectonic plates to recycle nutrients, and of course, a chemical composition compatible with known biochemical processes. It is a delicate balance where the synergy between elements can transform an ordinary rocky planet into a fertile world for life. Our own solar system illustrates the importance of this zone. Earth orbits precisely within the Sun's ideal range, where the global average temperature allows for oceans, rivers, clouds, and a complete hydrological cycle. Venus, although similar in size to Earth, is slightly closer to the Sun. As a result, its dense atmosphere, composed mostly of carbon dioxide, generates a runaway greenhouse effect, raising temperatures to levels that can melt lead. Mars, by contrast, sits on the outer edge of the habitable zone. Although it shows signs of having been warmer and wetter in the past, today it is a frozen desert, with a thin atmosphere that cannot retain heat or sustain liquid water on the surface for extended periods. This planetary trio demonstrates that simply being in the habitable zone is only the beginning. Geological history, atmospheric dynamics, and time are also key. Another fascinating aspect of the Goldilocks concept is its flexibility. Scientists now propose alternative habitable zones, such as tidal habitable zones, found on moons of giant planets like Europa and Enceladus, where the gravity of the parent planet heats the moon's interior, maintaining subsurface oceans beneath layers of ice, even far from the classical solar habitable zone. There is also the idea of habitability on rogue planets, those not orbiting any star, that may have enough internal heat to preserve pockets of liquid water beneath their surfaces. These possibilities dramatically expand the definition of habitability, suggesting that life may exist in environments previously deemed unlikely. Thus, the concept of the habitable zone is a cornerstone of modern astrobiology, but it is far from being a fixed measure. As we discover worlds with diverse compositions, exotic atmospheres, and complex orbital interactions, we begin to realize that life may not require a perfect balance like Earth's. Perhaps there are forms of life that thrive in extremes, that breathe methane instead of oxygen, that grow under the red glow of a dwarf star, or in the total darkness of an ocean buried beneath kilometers of ice. Still, the Goldilocks zone remains our primary initial reference, that narrow band between fire and ice where, at least here, life found its home. A planet's atmosphere is like an invisible mirror of its biology. Every element, every gas, every chemical trace in the gaseous layer surrounding a world is the direct result of the interaction between its soil, stellar radiation, geological cycles, and, perhaps, its biology. The search for extraterrestrial life, whether intelligent or microbial, has taken a qualitative leap in recent decades by understanding that the answer to the question, "Are we alone?" may not lie in radio signals or interstellar visits, but in the meticulous analysis of the atmospheres of distant worlds. Atmospheric spectroscopy has become one of modern astrobiology's most powerful tools, allowing scientists to read the chemical composition of exoplanets, even those dozens or hundreds of light years away, and likely never physically visited. If there are beings breathing, fermenting, or metabolizing on those planets, even if they are microbes, their traces may be imprinted in the air that surrounds them. The core idea behind detecting life via atmospheres is the search for what scientists call biosignatures, that is, chemical combinations that are unlikely to persist continuously without biological processes. A clear example is oxygen. Although this gas can be produced geologically, its maintenance in high concentrations, as on Earth, depends on constant biological activity. Another example is methane. On Earth, a significant portion of atmospheric methane is generated by biological processes, especially by methanogenic archaea, primitive microorganisms that live in anaerobic environments. When oxygen and methane coexist in the same atmosphere in large amounts, this indicates chemical disequilibrium, suggesting some form of active replenishment. In other words, something alive maintaining that composition. With the James Webb Space Telescope, this approach gained unprecedented power. Webb can detect light spectra passing through an exoplanet's atmosphere during its transit, that is, when it passes in front of its star as seen from Earth. As starlight travels through the planet's atmosphere, It undergoes subtle changes that reveal the presence of specific gases. This process is incredibly delicate and demands extremely advanced technology, but it is already underway. In 2023, for example, observations of planets such as K2-18b revealed the presence of water vapor and carbon dioxide, raising the possibility of hydrogen-rich environments with potential for microbial life. Although no definitive biosignatures have been found yet, the expectation is that in the coming years, with longer and more precise observations, atmospheres with distinct biochemical patterns may emerge from the data. Beyond gases, scientists also monitor variations in temperature, atmospheric pressure, and seasonal cycles on these planets. Cyclical changes in atmospheric composition, for instance, may indicate processes similar to photosynthesis, respiration, decomposition, or even the production of industrial pollutants. The latter has become so intriguing that it led to the concept of atmospheric technosignatures, signs of industrial or technological activity, such as the presence of chlorofluorocarbons, CFCs, synthetic compounds, that on Earth are produced exclusively by industrial civilizations. Though still highly speculative, this type of detection would be a direct signature of an advanced civilization. Another key factor is the type of star the planet orbits. Red dwarf stars, for instance, are highly active and emit large amounts of ultraviolet radiation, which can drastically impact the atmospheric chemistry of nearby planets. Atmospheres that endure in such environments must have protective or regenerative mechanisms, raising new questions about biological resilience and possible evolutionary adaptations. If life exists in such worlds, it may have developed entirely different strategies from those on Earth to handle radiation, extreme temperatures, and irregular light cycles. At the heart of this investigation lies a powerful idea. If we cannot see living beings on other planets directly, perhaps we can see the effects of their existence. In this context, atmospheres become chemical windows into life. They reveal not just the possibility of habitable environments, but complex patterns of imbalance that on Earth have always been associated with the presence of biology. And it is precisely that imbalance we seek, the signature of the unexpected, the out of equilibrium, the living. For if we one day detect an atmosphere with unmistakable traces of biological activity, even if invisible to the eye, we will know that we are no longer alone. The silence of the universe, once absolute, will be broken by a whisper, and that whisper will come from the chemistry of another world's air. Among all the celestial bodies in the solar system, none sparks as much fascination in the search for life as Mars. Seen from Earth, the red planet appears as a barren sphere, swept by dust storms and marked by frozen deserts. But that superficial image hides a radically different past. Billions of years ago, Mars was a wet world, with lakes, rivers, and possibly a vast ocean in its northern hemisphere. Geological evidence collected by multiple robotic missions, including the Spirit, Opportunity, Curiosity, and Perseverance rovers, confirms that liquid water once flowed abundantly across its surface, and where there is water, there is the possibility of life. Not complex life as we know it, but simple microbial forms adapted to extreme environments, like those thriving today in dark caves, thermal springs, or beneath Earth's polar ice caps. The history of Mars is a story of loss. During its first billion years, the planet retained a denser atmosphere and surface temperatures capable of sustaining stable liquid water. But being smaller than Earth and having a weak magnetic field, Mars eventually lost its atmosphere to space, swept away by the solar wind. As a result, temperatures plummeted, water evaporated or froze, and the planet became increasingly inhospitable. Yet the key question remains, did life ever emerge during that favorable period? And if so, could it still exist, hidden underground, protected from the cold and the surface's intense radiation? That is precisely what modern missions are attempting to discover. The Curiosity rover, operating since 2012, identified complex organic molecules in ancient sedimentary rocks in Gale Crater, indicating that the basic building blocks of life were once present. More recently, Perseverance, which landed in Jezero Crater in 2021, has been collecting samples that will eventually be returned to Earth by a joint NASA and ESA mission. Jezero was chosen because it once hosted a river delta, an ideal environment for preserving biological signatures. The rover is equipped with instruments capable of analyzing local mineralogy in extremely high resolution and searching for microscopic structures that might represent fossilized microorganisms. Another crucial point is the potential existence of underground liquid water. In 2018, radar data from the ESA's Mars Express orbiter suggested the presence of a salty lake beneath the planet's south polar ice cap. Although controversial, this discovery reignited hope that protected subsurface environments might harbor life. The analogy with Earth is direct. On our planet, microbial communities thrive kilometers below the surface, feeding on minerals, geothermal heat, and chemical compounds without any contact with sunlight. Mars could, in theory, offer similar conditions in pockets of briny water beneath its surface, especially if there are still residual heat sources from the planet's interior. Beyond direct searches, scientists also analyze Martian meteorites found on Earth. One of the most famous, ALH 4001, gained worldwide attention in 1996 when a NASA team announced the possible presence of fossilized bacterial structures. Although the interpretation was later disputed and alternative geochemical explanations proposed, the case placed Martian astrobiology at the forefront of public and scientific interest, fueling new missions and analytical models. The study of these meteorites shows that even without landing on Mars, we can still investigate its biological history through fragments that traveled across space and landed on our planet. Despite decades of research, Mars has yet to offer definitive proof of life, either past or present, but the accumulated data increasingly points to a planet that, in its youth, had everything necessary to support simple life forms. If such forms truly existed, they may have left behind chemical traces or fossils buried in Martian soil. Or, in an even more intriguing possibility, perhaps some microbial lineage survived the environmental collapse, retreating underground, where it may still persist today in a minimal hidden existence beneath the planet's surface. If we one day find such life, it could teach us how biology behaves in extreme environments, and more importantly, whether life is a common cosmic phenomenon or a statistical miracle that happened twice on two neighboring planets. If Mars represents the search for traces of a past life, frozen in time and buried in the soil, the icy moons of Jupiter and Saturn lead us to an even more extraordinary possibility: the existence of liquid, active, and potentially habitable oceans hidden beneath kilometers of ice. Among these moons, two stand out prominently in the field of astrobiology: Europa, of Jupiter, and Enceladus, of Saturn. Both present strong evidence of subsurface oceans kept in a liquid state thanks to heat generated by tidal forces, the gravitational stress exerted by their massive host planets. And in those deep, dark oceans, cut off from sunlight, life may have found a refuge. Not intelligent or complex life, but simple organisms, like extremophile bacteria that, on Earth, thrive in similar conditions, without light, under extreme pressure, and fueled not by photosynthesis, but by chemical reactions. Europa is perhaps the most promising world in the solar system when it comes to potential habitability beyond Earth. Its surface is a crust of ice crisscrossed by fractures and tension lines, suggesting continuous geological activity. Observations by the Galileo spacecraft and, more recently, by the Hubble Space Telescope indicate the presence of water vapor plumes being ejected from its south pole, further supporting the hypothesis of a global liquid ocean beneath its frozen shell. This ocean, which may contain twice as much water as all of Earth's oceans combined, is believed to be in contact with a rocky core, enabling chemical reactions similar to those found at hydrothermal vents on Earth's seafloor. On our planet, such vents host vibrant ecosystems full of organisms that live without sunlight, sustained solely by chemical energy and minerals. If similar processes occur on Europa, life could have quietly flourished for billions of years, below a surface our eyes have never seen. Enceladus, though smaller, is equally fascinating. The Cassini mission, which orbited Saturn for over a decade, accomplished something remarkable. It flew through the plumes of vapor erupting from Enceladus's south pole and analyzed them directly. The data revealed the presence of ice particles, water vapor, salts, and complex organic compounds. Even more significant, signatures of hydrocarbons and evidence of hydrothermal activity at the ocean floor were detected. This means Enceladus not only has liquid water, but also the fundamental chemical conditions for biological reactions, exactly like Earth's deep-sea hydrothermal systems. It is therefore one of the few places beyond Earth where life, even microbial life, seems more a matter of time and technology than pure speculation. These hidden oceans challenge our traditional understanding of habitability, which for decades was tied to the Goldilocks zone, the region around a star where water could exist in liquid form on a planet's surface. But Europa and Enceladus demonstrate that life may exist far beyond that zone, as long as there is internal heat and liquid water. That heat does not come from the sun, but from the gravitational friction caused by interactions with the planets they orbit. It is a powerful reminder that the universe may have created multiple pathways to life, and that the terrestrial model is only one among many. Science is now advancing toward direct investigation of these worlds. Missions like NASA's Europa Clipper, scheduled for launch in the second half of the 2020s, and ESA's JUICE, Jupiter Icy Moons Explorer, aim to map Europa's surface in high resolution, study its plumes, and assess the properties of its internal ocean. As for Enceladus, proposals are underway for future probes to return to its south pole and conduct even deeper analysis of the ejected particles, perhaps using technologies capable of directly detecting biologically associated molecules such as lipids, proteins, or nucleic acids. The presence of liquid oceans beneath icy layers reinforces the idea that life is not necessarily a surface phenomenon. It may be that in the universe, biology favors shadows, extreme pressures, and geothermal heat. Perhaps the most common forms of life do not walk beneath open skies, but navigate in total darkness, guided by senses we do not yet understand, feeding on elements we have never tasted. And if life truly exists on Europa or Enceladus, that discovery would not only prove we are not alone, it would radically expand our understanding of what it means to be alive. In worlds where silence is absolute and the sun is only a distant memory, perhaps something already breathes, grows, and exists, awaiting its first encounter with the eyes of human science. Imagine if the seed of life did not sprout here on Earth, but arrived from space, hidden inside a rock that drifted through interstellar emptiness until it collided with our primitive planet. This is the essence of the panspermia hypothesis, the idea that the fundamental building blocks of life, or even extremely resilient microbial forms, may have formed elsewhere in the cosmos and been transported here via meteorites, comets, or cosmic dust. Although the idea has ancient philosophical roots, first suggested in ancient Greece by Anaxagoras, it was only with advances in astrobiology and space chemistry that it began to be treated as a scientifically respectable hypothesis. One of its strongest foundations lies in something truly surprising: the presence of amino acids and complex organic molecules in meteorites that have fallen to Earth. Amino acids are the basic units of proteins, molecules essential to all known forms of life. In the 1960s, when the Murchison and Murray meteorites fell in Australia, scientists discovered more than 70 different types of amino acids in them, many of which are not found in terrestrial organisms. The Murchison meteorite, in particular, became one of the most studied objects in planetary science history. Later analyses revealed not only amino acids, but also nucleobases, components of RNA and DNA, alcohols, hydrocarbons, and even compounds with sugar-like structures. Even more intriguing was the discovery that these compounds had isotopic characteristics, confirming their extraterrestrial origin, ruling out the possibility of Earth-based contamination. The presence of amino acids in meteorites proves that the ingredients of life can form naturally in space environments. And these environments are not rare. Interstellar dust clouds, icy comets, primitive asteroids, and star-forming regions provide ideal conditions for complex chemical reactions, often catalyzed by cosmic rays or ultraviolet radiation. In Earth laboratories, scientists have successfully simulated these conditions and produced amino acids from simple compounds like ammonia, methane, and water exposed to radiation. This shows that the processes needed to form life's building blocks are not exclusive to Earth. They may, in fact, be widespread in the universe. The panspermia hypothesis unfolds on several levels. Passive panspermia suggests that organic compounds traveled inertly, protected inside meteorites, until they reached Earth. Directed panspermia, a bolder and more speculative idea, proposes that advanced civilizations could have deliberately spread life-seeding materials to other worlds. Even more compelling is the idea of natural panspermia between neighboring planets. Strong evidence suggests that fragments from Mars were launched into space after asteroid impacts and later fell to Earth. If Mars once hosted life, microorganisms could have been transported between planets, accidental passengers aboard space rocks. Microorganisms known as extremophiles, such as those of the species Deinococcus radiodurans, have demonstrated the ability to survive extreme conditions of radiation, vacuum, freezing, and heat, all present in space. Experiments conducted aboard space stations have shown that some bacteria can survive for months or even years outside Earth, especially if shielded by mineral layers. This reinforces the plausibility that primitive microorganisms could survive an interplanetary journey, entering a dormant state and reactivating upon encountering a suitable environment, such as a moist, geologically active planet. If life on Earth began with organic matter delivered from space, it changes not only our understanding of our origins, but also suggests that life may be a widely distributed phenomenon in the universe. Earth would no longer be a starting point, but rather a stopover, a rest station on a much longer cosmic route. This perspective does not invalidate the complexity of life's emergence on Earth. It simply shifts the stage of the first act to a much greater arena: the stars, the comets, the infancy of the universe. While the panspermia hypothesis cannot yet be confirmed by direct evidence of extraterrestrial life, it establishes a powerful link between astrophysics, chemistry, biology, and planetary geology. In a universe filled with wandering rocks, organic molecules, and diverse environments, the possibility that life is an ancient traveler quietly spreading between worlds is as fascinating as it is comforting. Perhaps one day, by analyzing an ice fragment from a distant moon or dust from a comet, we will find there the DNA of a story that began long before Earth, long before time. The story of life as a pilgrim of the cosmos. The biology we know is a carbon-based biology. Every form of life on Earth, without exception, is built from organic molecules based on this versatile element, which forms long chains and complex structures essential for proteins, DNA, lipids, and sugars. In addition, water is the universal solvent in which life's chemical reactions occur. But is this the only possibility? Could there be, somewhere in the universe, forms of life that do not follow Earth's rules, built from different chemistry, different elements, different solvents? This is the core of the idea of alternative biochemistries, the possibility that life in its essence is broader and more diverse than the single example we have, ourselves. Science has already identified several elements that could theoretically substitute carbon as the foundation of life. Silicon, for instance, is often cited as a viable candidate. It sits just below carbon on the periodic table and shares some of its bonding properties. In fact, silicon compounds can form complex three-dimensional structures. However, silicon also has limitations. It tends to form molecules that are less stable, less versatile, and less soluble than carbon-based ones, especially in aqueous environments. Still, on planets with lower temperatures or atmospheres rich in substances like methane or ammonia, silicon chemistry could be more favorable, potentially giving rise to an entirely different kind of life. Another possibility lies in replacing water as the solvent. Instead of a water-based world, imagine a world where oceans are composed of liquid methane or ethane, like the surface of Titan, Saturn's largest moon. Titan has lakes of hydrocarbons and a thick atmosphere rich in complex organic compounds. The Cassini mission identified organic molecules there that could, in theory, be precursors to cellular structures in non-aqueous environments. In 2015, NASA researchers even simulated Titan-like conditions in a laboratory and proposed the existence of structures called azotosomes, vesicles that could function similarly to Earth's cell membranes, but composed of materials compatible with solvents like methane. This opens up the real possibility that even without water, life's chemistry could emerge in cryogenic environments. Beyond silicon and hydrocarbons, there is speculation about biochemistries based on sulfur, phosphorus, or even metals. On Earth, certain extremophile microorganisms have already shown a remarkable ability to incorporate toxic elements into ordinary life. A famous example is the GFA-J1 bacterium, discovered in a highly saline and arsenic-rich lake in California. For a time, it was believed that it could substitute phosphorus with arsenic in its DNA, although this claim was later disputed. Even so, the discovery demonstrated that biochemistry may be more flexible than we imagined. Other extremophiles live in environments rich in sulfuric acid, intense radiation, extreme temperatures, or crushing pressures, places once thought completely inhospitable. The lesson from them is clear. Life always finds a way, even when that way is unexpected. The implications of life based on alternative biochemistries are profound. On one hand, they expand our definition of habitability. On the other, they make detecting life far more complex. Our instruments are calibrated to search for biosignatures based on what we know: oxygen, methane, water, carbon. But life that breathes hydrogen, metabolizes selenes, or dissolves in liquid methane could go completely unnoticed, even if it's right before our eyes. This has led scientists to propose the concept of shadow life forms that may exist on Earth or other planets, but remain invisible to our current detection methods because they are chemically so different from conventional life. Astrobiology, therefore, must be both exploratory and humble. Exploratory in testing the extreme limits of chemistry and investigating hypotheses in exotic conditions. Humble in recognizing that life may be far more creative than our predefined categories. If we discover life beyond Earth built on different elements, it will not only be a scientific breakthrough, it will be a philosophical revolution. It would prove that life is not just a chemical accident of carbon, but a natural tendency of the universe, something that arises whenever there is energy, complexity, and enough time, regardless of the exact ingredients. This conceptual openness redefines our search. We are no longer just looking for blue oceans and oxygen-rich atmospheres. We're looking for signs of organization, metabolism, and persistence, and perhaps one day, we will detect a form of life so different from our own that we will not even call it life, until it slowly, inevitably, reveals itself as what it always was, something just beyond the mirror of our biology. The search for life in the universe long ago left the realm of philosophical speculation and became a concrete, technological, and scientific endeavor. Spacecraft, probes, and telescopes cross the cosmos in multiple directions, each with its own objectives, but all sharing a common thread: to understand whether we are alone. Some of these missions directly investigate worlds within our solar system in search of biosignatures, while others explore the far reaches of the galaxy, hoping to detect habitable planets or atmospheres with suspicious chemical traces. Among them, several stand out as some of the most iconic and ambitious missions in human history: Perseverance, TESS, Rosetta, and the James Webb Space Telescope, JWST. Together, these missions represent the forefront of modern astrobiology, each illuminating a different part of the vast cosmic darkness. The Perseverance rover, launched by NASA in 2020, landed on Mars in early 2021 with a clear goal: to search for signs of past life. It is the most advanced mobile laboratory ever sent to another planet, equipped with instruments capable of performing high-resolution chemical and spectroscopic analyses. Its landing site, Jezero Crater, was carefully chosen for being the dry bed of an ancient river delta, an environment that on Earth is ideal for preserving microbial fossils. Perseverance not only explores the Martian soil, but also collects samples that are sealed and stored for a future mission to return them to Earth, scheduled for the next decade. The hope is that these samples may reveal microfossils or complex organic compounds indicating that Mars once hosted life. TESS, the Transiting Exoplanet Survey satellite, launched in 2018, is a planet hunter. Its mission is to detect exoplanets by observing dips in the brightness of nearby stars as a planet passes in front of them, a method known as a transit. While TESS is not directly an astrobiology mission, it is crucial for identifying the most promising worlds that can later be studied for biosignatures. So far, TESS has identified thousands of exoplanet candidates, including several located in the habitable zone of their stars. These targets, in turn, become priorities for more detailed observations with more powerful telescopes, especially the James Webb. The Rosetta mission, meanwhile, marked a remarkable chapter in the history of space exploration. Launched by the European Space Agency, ESA, Rosetta entered orbit around Comet 67P Churyumov-Gerasimenko in 2014, and, with the help of the Philae lander, performed the first controlled landing on a comet. Rosetta's astrobiological relevance lies in the fact that comets are natural preservers of primordial material, true time capsules containing the fundamental building blocks of life. Rosetta found amino acids, simple sugars, and even phosphorus on the comet, showing that complex organic compounds can form and survive in deep space. These findings support the idea that life, or at least its ingredients, may have been seeded on Earth by cosmic impacts, as proposed by the panspermia hypothesis. Finally, the James Webb Space Telescope JWST is so far the most sophisticated tool ever created to investigate exoplanet atmospheres for signs of life. Equipped with ultra-sensitive instruments, Webb can analyze starlight as it passes through the atmospheres of distant planets during transits, detecting molecules such as water vapor, methane, carbon dioxide, and potentially oxygen and ozone. Moreover, JWST observes in infrared, allowing it to study planets hidden by cosmic dust and to probe the coldest and oldest regions of the universe. Its first data have already revealed complex atmospheres on planets like K2-18b and WASP-39b, with potential for unprecedented breakthroughs in observational astrobiology. These missions represent the convergence of cutting-edge technology with one of humanity's oldest questions. Perseverance digs through Mars's red soil in search of fossils. TESS scans the sky for planetary shadows. Rosetta showed that life seeds may exist in icy rocks from the solar system's dawn. And James Webb peers at worlds hundreds of light years away, trying to decode the chemistry of the invisible. Together, these probes and telescopes form the eyes, arms, and ears of humankind in its most fundamental quest to understand whether we are alone, and if not, where, how, and in what form our cosmic neighbors exist. In the silent vastness of the cosmos, life may hide in many ways, underground, microscopic, or invisible to our chemical senses. But what if, instead of searching for microorganisms or molecules, we started looking for something that only a technological civilization could produce? This is the foundation of the concept of techno-signatures, detectable evidence of alien technology, signs left by advanced civilizations that, like us, transform their surroundings, build complex structures, transmit information, and generate energy on a large scale. Unlike biosignatures, which seek to identify life in its most primitive state, techno-signatures aim for the top of the evolutionary ladder, searching for signs of active intelligence that has reached a high enough technological level to impact the space around it. The most traditional method of searching for techno-signatures is through radio astronomy. Programs like SETI, Search for Extraterrestrial Intelligence, launched in the 1960s, scan the sky for artificial radio or microwave signals coming from specific points in space. The idea is simple. An advanced civilization might use radio waves to communicate or even broadcast information deliberately, and those signals would have patterns that differ from the natural radiation emitted by stars or cosmic phenomena. The famous WOW signal, detected in 1977 by a radio telescope in Ohio, was one such event, an intense, brief, and unexplained transmission that never repeated. Although it has not been confirmed as a techno-signature, it remains a symbol of what we're searching for, something artificial, unexpected, and deliberate. But techno-signatures go far beyond radio signals. With the advancement of astronomy, new ideas have emerged. One of the most discussed is the Dyson sphere, a hypothetical structure that a Type II civilization on the Kardashev scale might build around its star to capture all its energy. While we don't know if such a feat is possible, the presence of a Dyson sphere would create detectable observational signatures. The star's light would be altered, partially obscured, and there would be an excess of infrared radiation, the waste heat of such a megastructure. Modern telescopes are already analyzing unusual variations in stellar brightness, as in the intriguing case of Tabby's star, KIC 84628552, whose light dims irregularly and inexplicably, sparking temporary speculation about alien structures in orbit. Another emerging field is the study of artificial atmospheric pollutants. On Earth, compounds like CFCs, chlorofluorocarbons, are produced exclusively through industrial activity. If we were to detect these compounds in an extraterrestrial atmosphere, it would be a near-definitive indication of technology. The James Webb Space Telescope and its successors are beginning to have enough sensitivity to investigate this kind of signature in distant exoplanets, especially those in the habitable zone. The presence of artificial light, such as cityscapes visible from space, or even orbital structures like large satellites, also enters the realm of potential techno-signatures, though still very difficult to detect with current technology. In addition, there's the search for mathematical signals or encoded algorithms in transmissions, something that would indicate intentionality. Mathematics is a universal language, and patterns like sequences of prime numbers, pi, or specific ratios are considered strong candidates for interstellar communication. The idea is that an advanced civilization wishing to be discovered would use means recognizable by other intelligences, creating a kind of message for whomever finds it. Techno-signatures also raise a delicate issue: temporality. Even if many advanced civilizations exist in the universe, their detectability window might be short. They might destroy themselves, shut down their communication systems, or migrate to non-detectable forms of existence, such as digital civilizations operating at microscopic scales. In this sense, time may be the greatest obstacle. We may be at the beginning of our technological trajectory, while other species came and went millions of years ago, leaving behind only faint and incomprehensible traces. The search for techno-signatures is therefore both scientific and philosophical. It is the attempt to find not just life, but someone out there, someone with consciousness, curiosity, language, and engineering. It is the clearest mirror of our desire for cosmic contact and belonging. And even if we never find a definitive techno-signature, the very act of searching tells us something profound, that we believe we are not alone, that we have hope for dialogue, and that our science, increasingly precise, continues to turn its eyes and ears to the sky, listening for any noise that breaks the silence of the stars. The universe is 13 billion years old. Earth has existed for 4.5 billion. Stars are born and die constantly. Planetary systems are common. And life, at least on this planet, emerged quickly, flourishing in stunning diversity. And yet, throughout this vast expanse of space and time, all we hear is absolute silence. No reply, no confirmation, no unmistakable sign that there is something or someone out there. This deep, persistent cosmic silence is one of the greatest enigmas of modern science. And for many thinkers and scientists, it may have a grim explanation: the Great Filter Hypothesis. Proposed by economist Robin Hanson in the 1990s, the idea of the Great Filter suggests that somewhere between inorganic matter and an advanced interstellar civilization, there is an almost insurmountable barrier, a step in the evolutionary ladder so improbable or dangerous that almost no form of life is able to overcome it. This filter might be behind us, which would mean we've already passed the hardest part and are in fact rare and special. Or, far more unsettling, the filter could still be ahead of us, suggesting that every technological civilization is doomed to disappear before it can reach cosmic maturity. To understand the Great Filter, one must imagine the timeline from the emergence of life to its cosmic potential. We start with simple organic molecules, which eventually organize into cells, then into multicellular organisms, leading to intelligence and, ultimately, the technological ability to modify planets, explore space, and leave detectable marks on the universe. At what point in this chain is the filter located? Could it be that the emergence of life itself is the rare event? Or is the transition to multicellular organisms the improbable leap? Or perhaps conscious intelligence is so unlikely that Earth is the statistical exception of the entire galaxy? Some believe that the filter lies precisely where we are now, the threshold between mastering technology and surviving it. Civilizations that reach the ability to produce nuclear weapons, manipulate their climate, edit their genomes, and explore artificial intelligence also come dangerously close to self-destruction. If there is a filter ahead, it might lie in the very complexity of civilization. Perhaps it is impossible to maintain a balance between technological progress and societal stability long enough to become an interstellar species. This view, although pessimistic, serves as a powerful warning about humanity's future and our responsibility to the planet and to each other. In this context, The silence of the universe might not signal absence but failure, a dark echo of civilizations that came before, and for some reason, environmental collapse, war, runaway artificial intelligence, resource exhaustion, pandemics, or even cosmic events, failed to make it past the next curve on the evolutionary road. If that is what the silence tells us, then looking up at the sky is also looking inward, a constant reminder of our vulnerability. In this scenario, the great filter becomes less of a scientific hypothesis and more of an existential mirror. What do we do with our knowledge? Are we prepared for the responsibility that comes with it? On the other hand, if the filter is already behind us, then the silence takes on a new meaning. Perhaps life is extremely rare, and we are among the first civilizations capable of looking into the cosmos and trying to understand it. That would make us not survivors of a hostile universe, but pioneers of a future full of possibilities, a silence that does not represent absence but expectation, an emptiness waiting to be filled. Perhaps we are the first to cross the boundary, to build interstellar bridges, to light up a galaxy still asleep. The Great Filter hypothesis, therefore, is at once a scientific explanation, a cautionary tale, and an invitation to reflect. It forces us to consider that intelligent life may be as fragile as it is rare, and that every decision we make, social, political, ecological, or technological, carries the weight not just of the present, but of a possible shared destiny. If there are filters ahead, it is up to us to discover whether we've already overcome them, or whether we are still walking toward them unknowingly. Meanwhile, we continue listening, observing, building, and questioning, in silence, but not without hope. The discovery of life beyond Earth, whether microbial, plant-like, animal, or intelligent, would not merely be a scientific event. It would, above all, be a psychological, philosophical, and social earthquake, something that would redefine our identity as a species, shaking religious structures, worldviews, ideologies, and even notions of belonging. For the first time in human history, our cosmic uniqueness would be challenged by facts, not just beliefs. Earth would no longer be the sole stage of life, and humans no longer the only conscious protagonists. Even if the life discovered was simple, a fossilized bacterium on Mars, an active amino acid on Europa, or a trace of metabolism on a distant exoplanet, the symbolism of such a finding would far outweigh its scientific value. It would be confirmation that life is not an exception, but a natural rule of the universe, and that inevitably would shake the foundations of the human mind. The first impact would be emotional. The idea that we are not alone is one of humanity's oldest longings, but also one of the most frightening. Many people could react with euphoria, interpreting the discovery as a new chapter in human history, proof that we are part of something much greater. Others, however, might feel fear, a loss of meaning, or even existential panic. Psychology calls this an ontological shock, a rupture in the perception of reality so intense that the human mind struggles to assimilate it. Collective identity, the belief in the unique purpose of human life, and the foundations of cultural self-understanding would all be challenged. Even among the most rational, there would be a need to relearn how to place ourselves in the cosmos, now as one species among many, no longer at the center of everything. From a religious standpoint, the impacts would vary according to doctrine. Some religions might view extraterrestrial life as part of divine creation, an extension of God's work in other worlds. Others could enter into crisis, as their cosmologies built on Earth's centrality are contradicted by observable facts. Religious leaders would have to reinterpret scriptures, revise dogmas, and engage with scientific discoveries in unprecedented ways. In 2008, the Vatican officially declared that the existence of alien life does not contradict Catholic faith, stating that God's creative freedom cannot be limited. But not all religions are prepared for a revolution of this magnitude. Even non-theistic spiritual systems would have to grapple with new ethical, philosophical, and existential dimensions. In socio-political terms, the discovery of extraterrestrial life would cause global ripples. Governments, space agencies, and scientific organizations would need to develop international protocols for response, data transparency, and planetary protection. Fears of biological contamination or the emergence of collective panic would force containment policies and strategic communication. Global media would enter a state of continuous alert, and misinformation would spread rapidly. Conspiracy theories would gain traction, and trust in institutions could be tested to the limit. At the same time, a unifying potential would emerge. The perception that all humans share one planet, a single pale blue dot in the cosmic ocean. Instead of political and cultural divisions, perhaps a new sense of global belonging would arise, the birth of planetary consciousness. And what if the life discovered is intelligent? The scale of the impact would be even deeper. We would enter the post-contact era, even if the contact itself didn't involve direct communication, but merely the realization of their existence. Philosophers, linguists, anthropologists, theologians, and artists would have to reinvent their disciplines. How do we understand a mind that evolved on another planet under a different biology, history, and logic? How do we deal with the possibility that our civilization is not the most advanced, nor the only one? Ethical questions would emerge. Do we have the right to interfere with those worlds? How can we ensure that first contact is not destructive, as so often occurred in Earth's own history between distinct civilizations? On an individual level, the discovery of extraterrestrial life would act as an inner mirror. For many, it would reinforce the beauty of existence, the sense that we are part of a universal web that transcends time and space. For others, it could trigger anxiety, feelings of smallness, or loss of control over the future. The educational system would need to adapt, and popular culture would inevitably absorb the theme through films, books, music, and public debate. Science fiction would become an even richer ground for speculation, and art would strive to express the ineffable, the experience of knowing we are no longer alone. In short, the discovery of extraterrestrial life would be an unprecedented collective experience, a true dividing line in human history, not only because of the scientific evidence, but because of the transformation of our narratives, beliefs, fears, and hopes. It would change the way we look at the sky, and also the way we look at each other. It might be the beginning of a new era, where humanity, upon meeting the cosmic other, finally rediscovers itself. In a universe more than 13 billion years old, time becomes as relevant as space when discussing the possibility of finding life beyond Earth. Often, when we imagine other civilizations, we focus only on where they might be, on which planet, in which galaxy, at what distance. But an equally important and perhaps even more unsettling question is, when did they exist? Or more intriguingly, when will they exist? The hypothesis that humanity emerged at an offbeat moment in the great cosmic clock, too early to encounter other civilizations or too late to reach them, is one of the most fascinating and melancholic explanations for the silence we hear when looking at the stars. If intelligent life is rare, and its emergence requires a highly improbable chain of events, from the formation of rocky planets, through the evolution of multicellular organisms, to the appearance of consciousness, then perhaps we are among the first intelligent beings in the universe. This is known as the pioneer hypothesis. In this scenario, Earth and its technological civilization may be paving the way in a universe still biologically young. Though our planet is 4.5 billion years old, stars like the Sun will continue shining for billions of years to come. This means the most stable and long-term habitable planets may not have even reached their peak capacity to support life. Life may just now be beginning to emerge on many worlds, and advanced civilizations may still be in their infancy, or yet to be born. In that case, the cosmic silence would be just a pause before the great interplanetary symphony. A natural silence, like the hush of a theater before the first note of a symphony. On the other hand, perhaps we have arrived too late. That other civilizations arose billions of years ago, evolved, developed, explored space, and disappeared. In this view, the universe may once have been inhabited by consciousness, cultures, entire societies that collapsed from natural or self-destructive causes, leaving only traces, cosmic dust, and ruins we have not yet detected. The galaxy would be like a fossilized forest, with trees that once bloomed, but whose seeds did not survive time. This hypothesis aligns with the idea of the Great Filter. Maybe most civilizations do not last long enough to leave enduring marks or to establish contact with others. They appear, shine briefly, and vanish, like solitary fireworks in the midst of infinite darkness. There's also an intermediate possibility. Perhaps we're simply in the wrong window of time. The duration required for an interstellar message to cross the galaxy can span thousands of years. If a distant civilization sent us a signal, it might still be on its way, or perhaps we missed it by decades or centuries, a tiny fraction in cosmic terms, but enough to render us unable to detect their existence. Communication between civilizations may be extremely rare, not just for technological reasons, but because their timelines never align. Being in the universe in this sense is like standing on a vast beach hoping another person waves, but being in time zones so misaligned that we never see the same sunset. The temporal issue also touches on another delicate point, our urgency. Humanity lives in a rapidly changing cycle, in an era where technology transforms in decades what once took millennia, but the universe operates on a much slower scale. Stars live for billions of years. Galaxies collide over spans that last epochs. Compared to that, our centuries are mere instants. It is possible that intelligent life is a phenomenon that flares and fades quickly, a kind of biological spark in a universe that sleeps deeply between those rare flashes. If so, the only real contact may be with the past, through ruins, ancient signals, dead technologies. The universe's present may be empty, even if its past was full of voices we failed to hear in time. And what if intelligence is still to come? What if the true era of cosmic consciousness hasn't even begun, and we are part of the inaugural generation, primitive beings who, one day, will be remembered by more advanced civilizations as the cosmic ancestors? In that scenario, we are planting the seeds of an interplanetary future, where other intelligences, either created by us or emerging from elsewhere, will recognize themselves as part of the same existential tapestry. Time, therefore, is not just the backdrop of the search for extraterrestrial life. It is the protagonist. Perhaps we are alone for now, but not alone in the grand scheme. Perhaps life is still to come. Perhaps it already passed. Perhaps the universe is full of stories we can only hear after their authors are gone. And here we are, on this pale blue dot, still listening, trying to find in time what space has not yet revealed. In 1964, Soviet astrophysicist Nikolai Kardashev proposed a revolutionary scale to measure the technological advancement of a civilization based on a single criterion: the amount of energy that civilization is capable of controlling. More than a theoretical classification, the Kardashev scale has become a lens through which astrobiology, physics, and futurology examine the possible fate of intelligence in the universe. It does not merely tell us where we are, it hints at where we could go, and where others on distant worlds may already have arrived. The original scale proposed 3 levels, but over the decades, new categories have been added to expand this vision and contemplate possibilities that stretch the limits of imagination. A Type 1 civilization, according to Kardashev, is one that can use and store all the energy available on its home planet, including solar, geothermal, atmospheric, and even seismic resources. Today, humanity is still below that threshold. Physicist Michio Kaku estimates that we are a Type 0.7 civilization, meaning we harness a considerable fraction of planetary energy, but still depend on fossil fuels and lack full control over climate cycles, oceans, or the planet's core. Reaching Type 1 would require total mastery over natural systems, a global energy transition, and a socio-political stability that allows for the efficient and sustainable use of all planetary resources. A Type 2 civilization can control the entire energy output of its parent star. This would involve building megastructures, such as the hypothetical Dyson sphere, a network of satellites or reflectors orbiting the star and capturing its energy directly. With this level of power, a civilization could restructure entire planetary systems, move worlds from orbit, create artificial habitats with billions of inhabitants, and manipulate its cosmic environment at will. Such a society would be nearly omnipresent in its stellar system, visible from afar through its energetic techno-signatures, such as excess infrared emissions or unusually filtered starlight. A Type 3 civilization, in contrast, controls the energy of an entire galaxy. This leap in scale is incomprehensible to the human mind. It implies not only colonizing millions of star systems, but also manipulating stars, black holes, dark matter, and exotic forms of energy. A civilization of this caliber may have completely shed its original biological limits, potentially existing as distributed consciousness based on artificial intelligence, quantum computing, or structures unknown to us. Some theorists speculate that a Type 3 civilization might possess enough power to alter local physical laws, manipulate entropy, or even create bubbles of reality. The most unsettling question then becomes, if they exist, why don't we see them? In recent decades, thinkers like Carl Sagan have proposed extensions to the Kardashev scale, such as Type 4, which would control the energy of a supercluster of galaxies, and Type 5, capable of manipulating the energy of the entire observable universe. Some even speculate about Type 6 or 7 civilizations, which would operate across multiverses, controlling dimensions beyond known space-time. Although deeply speculative, these ideas help explore the evolutionary potential of intelligence and remind us that perhaps the universe is filled with structures and phenomena we simply do not recognize as technology because they lie far beyond our cognitive scale. However, this vision of progress also raises red flags. Between Type 0 and Type 1 may lie the most critical survival phase, the point at which a civilization develops enough power to destroy itself, but has not yet reached the technological or ethical maturity to protect itself. This puts humanity in a danger zone. The technological climb that could take us to Type 1 might also lead to extinction if not guided by collective responsibility, scientific education, and global governance. What makes the Kardashev scale so powerful is not just its mathematical simplicity, but its philosophical depth. It forces us to think about the future in cosmic terms. It asks, what is our place in time? What are our limits? And the most haunting, are there already Type 2 or Type 3 civilizations somewhere out there, watching silently, or are we the first to walk this path? Perhaps their creations are right before us, in anomalous galaxies, in the light curves we cannot explain, in the spectral data we overlook. Or maybe the emptiness around us is the echo of civilizations that tried and failed. Either way, to look at the Kardashev scale is to gaze into the mirror of possibility. A mirror that silently asks, will you make it? Faced with the profound cosmic silence, despite so many statistical and technological possibilities for the existence of other civilizations, a provocative theory emerges, unsettling in its simplicity. What if they are already watching us, but have chosen not to make contact? This is the essence of the zoo hypothesis, formulated in the 1970s by researcher John Ball, which proposes an intriguing analogy. Perhaps Earth and humanity are, in the eyes of more advanced civilizations, like animals in a cosmic zoo, being monitored from a distance for reasons we don't yet understand, under some sort of non-intervention protocol. Just as we do not deliberately reveal ourselves to isolated tribes on Earth to avoid interfering with their culture or development, a Type 2 or Type 3 civilization on the Kardashev scale might be applying the same principle to us. This hypothesis assumes that in an ancient and vast universe, it is highly unlikely that we are the first, or the only species, to reach a technological stage. If other intelligences do exist, but don't communicate with us, perhaps it is because they have chosen not to. Their motivation for remaining silent could be ethical, scientific, or strategic. It may be that advanced civilizations have established galactic agreements prohibiting contact with pre-technological species, and from their point of view, we may still be primitive, violent, unstable, and self-centered. This kind of cosmic quarantine would prevent us from receiving any form of information, signal, or interference that could alter our evolutionary path. In other words, we may be under silent observation, part of a larger experiment, or worse, deemed unfit to join the galactic community. The galactic quarantine hypothesis complements the zoo paradox, suggesting that there may be a cultural, technological, or philosophical barrier imposed by these civilizations to keep us isolated until we demonstrate sufficient maturity. But maturity in what terms? Ethical, environmental, social? Perhaps the criterion for contact isn't just technological advancement, but the ability to preserve one's planet, resolve internal conflicts, eliminate weapons of mass destruction, or show genuine interest in other forms of life, something that for now seems more aspirational than real. We might be seen as a risk or as a civilization in transition that has not yet proven itself trustworthy. This theory, though speculative, touches on a deeply philosophical point: cosmic humility. It forces us to consider the possibility that we are not the protagonists of the universal story, merely temporary observers on a much greater stage, still denied access to the backstage. Worse yet, we may be surrounded by evidence we are incapable of interpreting. If a civilization wanted to hide from us, it would have the means to do so. It could use cosmic camouflage, gravitational distortions, quantum encryption, or manifest only in frequencies we cannot detect. In this scenario, the absence of evidence would not be evidence of absence, but the result of deliberately imposed isolation. There's also a darker version of this hypothesis. What if we have already been contacted, but the signals were ignored, misinterpreted, or deliberately hidden? Throughout history, accounts of unexplained phenomena, mysterious lights in the sky, strange sounds, and myths of beings descending from the heavens appear in different cultures around the world. While science often dismisses these as natural or folkloric, the zoo hypothesis suggests that some may be remnants of subtle contact, tests, or long-term observation. And perhaps humanity is constantly being tested and failing. However, a more optimistic reading exists. In this case, the silence could be protection. Advanced civilizations might know that the universe is a hostile place, full of technological predators, and choose discretion not out of disinterest, but for self-preservation. To reveal themselves might attract danger. Therefore, they maintain silence as a survival strategy, and as a precaution, extend that protection to developing planets like ours. Earth, in this scenario, would be part of a silent network. Monitored, yes, but shielded, until it is ready to take its place on the cosmic map. Ultimately, the zoo paradox and the galactic quarantine hypothesis say more about us than about them. They reveal our longing for contact, our suspicion of abandonment, our desire to belong, and our fear of not being worthy. As we listen to the silence of the stars, perhaps the universe is simply waiting for humanity to look inward and prove, not with words or satellites, but with choices, that we are ready to be heard. And when that moment arrives, if it arrives, perhaps the zoo will become a forum, the quarantine an invitation, and the silence a reply. Since the dawn of modern science, one question has loomed in the background of all our investigations into the cosmos. Is life a statistical rarity or a natural inevitability? This dilemma is not merely scientific, it is profoundly existential. If life is an exception, an unlikely event that occurred only once on a peripheral planet orbiting an ordinary star, then we are a cosmic accident, an anomaly among trillions of failed possibilities. But if life is a universal rule, emerging wherever minimum conditions are met, then we are part of a fundamentally living universe, filled with microorganisms, exotic ecosystems, and perhaps civilizations that, like us, gaze at the stars in search of company. This debate remains open because, to this day, we have only one confirmed example of life: Earth itself. From a statistical standpoint, the argument that life is a rule is compelling. The Milky Way contains around 200 billion stars, and at least 100 billion planets, according to conservative estimates. Among these, billions lie within habitable zones with potential for liquid water. We also know that the basic ingredients for life, carbon, hydrogen, oxygen, nitrogen, and phosphorus, are widely distributed throughout the universe. Organic compounds have been found in comets, meteorites, interstellar clouds, and even in the atmospheres of exoplanets. If these ingredients are common, why would life be so rare? Evolutionary logic suggests that once life begins, it tends to expand, diversify, and persist. After all, life on Earth arose quickly after the planet cooled and has survived 5 mass extinctions, thriving even in the most extreme environments. On the other hand, the absence of any detection beyond Earth raises the unsettling possibility that life, while possible, is extremely rare. Perhaps the emergence of self-replicating structures is such an improbable event that Earth is a statistical outlier, the only planet where all factors aligned perfectly. This view is reinforced by the complexity of transitioning from chemistry to biology, from biology to intelligence, and from intelligence to technology. Each stage involves hurdles that few biospheres may ever overcome. Paleontologist Stephen Jay Gould, for instance, argued that evolution is deeply contingent, full of unpredictable forks. If the tape of life were rewound and played again, the outcome would likely be entirely different, and conscious intelligence might never appear. Some argue that life may be common but invisible to us. Perhaps it exists in forms we don't recognize as life, with alternative biochemistries based on silicon, ammonia, or non-aqueous solvents. It may thrive in environments we once considered uninhabitable, such as subsurface oceans, gas giant atmospheres, or even interstellar clouds. Our detection methods are inevitably biased by Earth biology. We search for oxygen, methane, carbon, water. But what if life breathes another gas? What if it grows on different timescales, speeds, or forms of awareness? In that case, the universe could be teeming with life, but we simply have not yet learned how to recognize it. The debate is also fueled by the absence of technological signals. If intelligent life is common, why don't we hear transmissions? Why don't we see megastructures? Why don't we detect unmistakable traces of Type 2 or Type 3 civilizations on the Kardashev scale? This absence has led to the Fermi Paradox, the great filter hypothesis, and the idea that intelligence may be self-limiting, a brief, fragile phenomenon that almost always collapses before expanding. It could be that life is common, but intelligence is the exception. Or the opposite, life is rare, but once intelligence arises, it inevitably becomes cosmic, and we are still waiting for that encounter. Science advances gradually, fragment by fragment. Discoveries of amino acids in meteorites, liquid oceans on icy moons, exoplanetary atmospheres with organic compounds, and terrestrial microorganisms that live without light, heat, or oxygen, all of these broaden the plausibility of life beyond Earth. But none has yet provided a second genesis, and that is exactly what we're missing, a second example. The definitive proof that life is not exclusive to Earth. It could be a microorganism on Mars, a fossilized cell on Enceladus, or an atmospheric trace on a distant exoplanet. With that second example, the debate will no longer be theoretical. The exception will become the rule, and humanity will, for the first time, see itself as part of a larger community, the community of the living in the universe. In the meantime, we remain torn between skepticism and hope, between the fascination of possibility and the weight of silence. Life as rule or exception is not just a scientific issue. It is a question about who we are, what it means to be alive, and whether the universe shares the same spark that pulses within us. And until that question is answered, we will continue listening, exploring, and imagining, because deep down the search for life out there is the continuation of our search for ourselves. At the end of all questions about planets, equations, filters, and signals, a silent, almost sacred truth remains. The search for life beyond Earth is, inevitably, a quest to understand who we are. Though disguised as a scientific and exploratory endeavor, this pursuit is also a spiritual, philosophical, and deeply personal journey. When we point telescopes at the sky, send probes to Mars, or listen to the silence of deep space, we are doing more than searching for aliens. We are trying to answer humanity's oldest questions. Where did we come from? Why do we exist? Are we alone? And if we're not, what does that say about us? Modern science has transformed this ancient longing into methodology, mission, and cutting-edge technology. But behind the sensors, formulas, and spectrometers, there are human hearts beating with anticipation. Each new exoplanet discovered, each organic molecule identified in a comet, each shadow recorded in the atmosphere of a distant world carries the silent hope that maybe, just maybe, we are not a solitary singularity, but a manifestation of something greater, a universe that creates life as a natural consequence of its own complexity. The search for life beyond Earth also shows how far we've come, and how much we still have to learn. For centuries we believed the universe revolved around us. Then we discovered we are just one among billions of planets. Now, we understand that even life itself may not be unique. This evolving perspective makes us more humble, more careful, more connected to the whole. Earth, seen from space, is a pale blue dot wrapped in fragility. Knowing that there may be other forms of life out there, even simple, microbial, or hypothetical ones, reminds us that life in all its forms is rare, precious, and vulnerable. And perhaps for that reason, it deserves to be protected, not only here but wherever it exists. This search also forces us to project forward. If we one day find life, or if we are the ones to bring it to other worlds, we will need to rethink our responsibilities. How will we treat other forms of existence? How will we balance scientific curiosity with ecological respect? Will we be ready to coexist, to engage, to share? Encountering the other, whether microbial or conscious, will demand an ethical, political, and cultural reinvention, and perhaps the greatest transformation won't happen out in space, but within ourselves. Because to realize that the universe might be alive is also to understand that we are part of something infinitely greater, mysterious, and interconnected. That is why, when we look to the skies for signs, what we are doing is deeper than scanning stars. We are acknowledging our desire for meaning, our hunger for belonging, our restlessness before the mystery. In this context, science is more than a method. It is a language of the human soul trying to decipher the codes of a cosmos that has yet to respond. But maybe, just maybe, it's waiting for the right moment to be understood. And even if we never find life beyond Earth, this search has already given us something priceless, a new way of seeing ourselves. It has taught us that we are fragile, yet incredibly resilient. That we are small, yet possess imaginations powerful enough to reach distant galaxies, if not with our feet, then with our minds. That we are alone, for now, but not abandoned, because in every listening effort, every launched probe, every captured image, what echoes is the certainty that life, and at least here, has enough courage to seek itself within the infinite. Thus the search for extraterrestrial life ceases to be merely an astrobiological investigation and reveals itself in its deepest essence as a declaration of identity. We search for life in the universe because deep down, we long to know if we belong to something greater. And maybe this search was never about them, but about us, about the miracle of existing, about the silence that shapes us, and about the eternal hope that somewhere in the sky there will be an answer worthy of the question that has moved us since the beginning. Who are we in this vast and mysterious universe?